Generators and motors both involve relationships between electrical energy and mechanical energy. A generator will convert mechanical energy to electrical energy, and a motor converts electrical energy to mechanical energy. To produce electricity from motion, engineers need sources of mechanical energy that are not only reliable, but they are plentiful and they are consistent over time. There are a lot of sources of mechanical energy that are intermittent, something like wind in a small area. It's usually, sometimes it's windy, sometimes it's not. In certain parts of the world, sun might not be a reliable source, or water in a drought prone area might not be a reliable source of energy. So, what is going to be an effective and reliable source of mechanical energy is going to vary from place to place and from uh, different conditions to other conditions. Anytime you have motion, mechanical energy in a fluid. So if you have a fluid flowing, a fluid is anything that flows. A fluid can be water, steam, air. Anytime you have a fluid flowing and it turns a motor, it can convert the the mechanical energy of the fluid into rotational energy of a rotor, and thus turning a turbine. A turbine is a it's a device that converts that mechanical energy, which is usually in one direction or linear. It converts mechanical energy into rotational energy. Turbines are incorporated in the design of different electrical generators, and they involve the spinning of either a coil or magnets that are close to a coil. When you put a generator in the path of a naturally occurring motion, then you can find some pretty predictable and uniform motion. Here we see three examples. The first example shows a hydroelectric plant. Hydroelectric plants are frequently incorporated into dams. By building dams, people are able to control the flow of rivers and let water flow through the dam and turn turbines and generate electricity as they see fit. It's only dependent on the replenishment of the water behind the dam. So in times of drought, the efficiency of dams can decrease. In the second picture, we see a, uh, a bunch of wind turbines, and we see these in the deserts frequently, the deserts of California, where there's not a lot of development, and there's a lot of open space and pretty consistent winds. So if you drive through those big turbine farms, you see that some turbines are turning and some are not. That's because they're all pointed in different directions, but they do require quite a bit of space in order to generate a significant amount of electricity, and they can only be put in certain places where it's windy, where there's a consistent amount of wind. So different uh, different plants, different types of turbines can be placed in different locations in the world. And lastly, this last picture may look a little more confusing. This is actually a tidal power plant. So the moon the moon's gravitational field causes the oceans to rise and fall. So as the oceans rise and fall, the there's a flow of water, and so this is a large turbine that is partially submerged in the ocean. And as the tide comes in, it causes this turbine to rotate and generate electricity. And as the tide goes out, it rotates the other way. And tidal power is incredibly reliable. The tides always go up and down. The the drawback of them is that they're very large, and well, they have an environmental impact. They take up the space in the ocean, and they also don't. You don't have as much movement. There's a tremendous amount of mechanical energy because there's a lot of water moving but in the tides, but the amount that it moves is not, you don't get as much movement over a short period of time as you do with a dam, with a river, or with wind frequently.